Professor Bialis here. In this video we're going to be covering section 11.3 where we solve equations using quadratic methods. Now what that means is we're going to be dealing with equations that aren't truly pure quadratics, but we're going to be able to either turn them into quadratics or break them down into a quadratic like pattern. Okay, so we're just going to kind of jump right into some examples. Some of these examples are going to be blasts from the past where we're talking about radicals or rational equations, but in this case they're going to turn into quadratics eventually. Now in the past when we did see a quadratic we always said it's factorable, it's factorable, it's factorable. That may not be the case here. Okay, so we have to keep an open mind with this. If they are factorable, I would suggest factor them, but if they're not, remember we have square root method, we have completing the square, we have quadratic formula. Okay, what I would suggest is always when you see a quadratic, get a 0 on one side and aim for factoring or aim for the quadratic formula. But try factoring first. But if the numbers aren't nice for you or it just doesn't factor, then you have that quadratic formula already set up so you can jump right into that. Okay, so let's look at some examples. So I just want you to solve, and we have this. Now, again, we're talking quadratics this whole chapter, but now I have a radical equation. So it's a radical equation. We need to approach it as such. So the first thing we do is get that radical isolated. Now that doesn't mean it has to be on the left or the right. It can be on either side, just isolated. So instead of moving the x and the 3, let's just move the radical. So I'm just going to add the square root of x minus 1 to both sides. And we have that. Okay, now I can get rid of that radical by squaring both sides. And this is where our quadratic is going to come from. So I'm going to FOIL this out. Again, if you need to, write it out twice so you can see that foiling that's going on. So I have x squared minus 3x plus 9. And then I can just drop out that x minus 1. Okay? Now, I'm going to clean this up a little bit. And then I can get that 0 on one side. Again, I personally like to still keep that habit of getting that 0, because then I can factor, I can use quadratic formula. I'm setting two different methods up at the same time. So I can subtract the x, add the 1. So x squared minus 7x plus 10 equals 0. Then I'm looking at this, I can factor that. So I'm going to say x minus 5, x minus 2. That multiplies to the positive 10, and those will add up to the negative 7. Again, if you want to go to the quadratic formula, that's fine, but you'd still be writing the formula down. Okay, this will be quicker when it's there. So x minus 5 is 0, x minus 2 is 0. I would add the 5, I would add the 2. And there we go. Okay, now remember, this was a radical equation. We have to check our answers because this step of squaring both sides may have thrown something off. So I'm going to go back all the way to the original here, plug in a 5. 5 minus 1 is 4, square root of 4 is 2, so there's a 2 here. So 5 minus 2 is 3, 3 minus 3 gives you your 0. And then I got this 2. 2 minus 1 is 1, square root of 1 is 1. 2 minus 1 is 1, 1 minus 3, not 0. So this is garbage. Okay? So, 5 is my only answer, we're good to go. Don't forget the rules that we had in the past. When this is a radical equation, you still have to check that thing, even though we were thinking of it as a quadratic halfway through. Okay, let's look at another one. Okay, here's another blast from the past. This is a rational equation. Okay, so what I'm going to do first is put that negative directly on those components of the numerator so I don't lose it. Then I want to clear those fractions out. So I'm going to clear by multiplying every term by the LCD. And we got that. This is gone. X times 2x is 2x squared. This is gone. And then I have this to FOIL. Now if how it's kind of stacked there throws you off, then just write it nicely underneath. That's what I'm foiling. Okay? So what I get is a negative x squared minus 2x plus x plus 2. Again, negative x squared minus 2x plus x plus 2. And then here, all that's gone. We got a 5. Okay? Now let's clean this up. 2 minus 1 is just a 1x squared. Minus x plus 2 equals 5. Again, I have a quadratic. I'm still going to go for that 0. I'm going to subtract a 5. And we have that. Okay? Now, I would look at that and say, can I factor that? There's no way I'm going to multiply to a 3 and then combine back to a 1. There's no way I'm going to have that happen. So I'm going to go into that quadratic formula. X is equal opposite of b plus or minus square root b squared minus 4ac all over 2a. Don't stop writing it down. Then I have opposite of b, so a positive 1, plus or minus square root b squared, so negative 1 squared minus 4ac all over 2a. And then I get 1 plus or minus square root of something over 2. Just write that down first. And then focus on this whole calculation here. So, like I said, negative and negative, that's going to be a positive. 4 times 1 times 3 is 12, so plus 12 at the end. 1 plus 12 is 13. And that's it. There's nothing to reduce on that radical. Here are your answers. Now remember, that answer right there needs to be checked to make sure it never gives you a 0 in the denominator. Okay? Now, this is not a nice number because of that square root of 13. We got that 1 plus root 13 over 2 and 1 minus root 13 over 2. That's going to be some irrational decimal. Okay? For this to be a 0, I would have to plug in a 1. That's not 1. Okay? So don't think, oh, I got to do all that calculation with that weird fraction. No, that's not 1. This is not going to be a 0, so we're safe. Okay? Same thing here. That's not 0. That's the only thing that would cause a problem there, so we're safe. Okay? Now, could that still be wrong? Yes, but if you're just checking for the 0 before you move on, don't think that you have to plug that in necessarily. You know what number you would have to have there for there to be a problem. That's not it. So we're good to go. We can move on. Okay? Let's look at another one. Now be careful here because this is not a quadratic. A quadratic would have to have an x squared as its highest power of x. Here we go all the way up to x to the 4th. Okay? Now, that means quadratic formula can't be used in this situation. You can't say this is a, b, and c. Because it's not a quadratic. Okay? But we can still factor if that's a possibility. So, what we're going to do, we got the 0 on one side. I'm going to think of this like a normal trinomial. Just a general trinomial, that's what it is, okay? Now, normally with x squared I go x and x. I divide it up evenly. Here, x to the fourth would be x squared and x squared. Now, a negative 36 would require opposite signs. And then I have a negative 9, positive 4. And there we have it. Okay? Now, with factoring, after I get that factoring done, I set each of those factors equal to 0. Okay? Now, in this case, I normally would think, okay, I need to factor this again. There's a difference of squares, so and so. But remember, we have that square root property as well. So I could do difference of squares here, but I couldn't factor this. I can use square root method on both of them. So I'm going to subtract a 4. And then take the square root of both sides. Now remember, plus or minus, square root of negative 4 is a 2i. And here we have it. Over here, I could do difference of squares or add the 9. And we got that. Okay? Now I want to point something out. When we had this x squared, we had a degree of 2. We had 2 answers. Here, we had a degree of 4. How many answers do we have? We had 4 answers, 2 and 2. So always look for that. That degree tells you how many answers you should be expecting. Especially when you're including complex answers, you should get that number. Okay? Let's look at another one. So again, when you have a power higher than 2, think factor. Think factor, because sometimes you'll factor, let's say it's an x to the third, you can factor one of those out, and then you can use quadratic formula. Okay, but still, first think of factoring. How about this? Okay, so you could technically just distribute the heck out of this thing, combine like terms, and then you get back to a standard normal quadratic, okay? However, there's a trick we can use to kind of streamline this process, okay? Now notice, these quantities are the same. If these were different, then you would have to just distribute and go that way. But since these are the same, let's use that. I'm going to put in what's called a let statement. So I am going to say let y, or any variable you want, just not x because it's already there. I'm going to use y. Let y equal that piece they have in common. Instead of saying x plus 4, I'm going to call it y. That's all. Okay? What I can do is I can then take this equation and substitute in that y. So I'm going to say y squared minus y minus 6 equals 0. Okay? Same equation, but instead of x plus 4, I'm just substituting in that y. Okay? And we created that y, but that's okay. We created it. We're holding true to it the rest of the way. Look at how much easier this is now. We could use quadratic formula or simply get y minus 3y plus 2. Look at how quick that was. As opposed to doing all that distribution, getting a problem like this, having to combine like terms, and then having to do some factoring. Okay? Now, setting each of these equal to 0, I can add the 3, and then here I can subtract the 2. Now this is the dangerous part about this. What we essentially did, think about, moving from one house to the other. Do you take one thing at a time when you're moving from one spot to another? No, you pack your stuff in boxes, you put it in a truck, you go across town or across the country, and then you unpack. Don't forget to unpack. We packed all of our stuff up nicely like this. We moved And now we have to unpack. We weren't asked for y. Y is something we just made up. We were asked for x. So unpack the box. So instead of y equals 3, I'm going to say x plus 4 equals 3. X plus 4 equals negative 2. So again, instead of just muscling through, distributing and all that stuff, I pack it in a nice little box, I move it across town, and then I unpack. And now I can get x is negative 1. X is negative 6. And there we go. Okay? In this case, you can always go back and check. It's not a necessity, but you can always go back and plug those into the original problem. Nothing here. Always check at the original. Okay? Let's look at another one. Okay. Now this is definitely not a quadratic equation. There's rational exponents there, so it is some sort of a radical equation, because remember, rational exponents can always be translated to radicals. However, we are going to do this using the same method that we used over here. We're going to use that let statement. So what we're going to do is we're going to take this mess and we're going to pack it in a nice clean box. Okay? So how do I do that? Remember, a quadratic always has like an x squared, then an x, then a constant. Or a y squared, then a y, then a constant. Or an x plus 4 squared, then an x plus 4, then a constant. Or an x to the 1/3 squared, an x to the 1/3, and then a constant. Okay? If this was like 5/7 and that's 1/3, that's a completely different ballgame. Okay? But when you have that connection between these two, notice I have the 1/3 here, and then this 2/3 can be thought of as 1/3 times 2. I can now see that these have the same base component. Okay? Now what I'm going to do is use that let statement again. So let that x to the 1/3 equal, I'm going to say y. Again, use whatever variable you want, just not x because it's already there. So instead of x to the 1/3 squared, I'm going to say y squared minus 7y plus 10 equals 0. And now I have a very normal basic quadratic. So I can factor y squared is y and y. I'm going to have a negative 5 and a negative 2. Those multiply to the positive 10, add to the negative 7. Then y minus 5 is 0. Y minus 2 is 0. Y equals 5 after I add it over. Y equals 2. We're not done though. Okay? This is very important. If you use a let statement, you got to unpack the box. So y equals 5 really means x to the 1/3 equals 5, and x to the 1/3 equals 2. Now this, how do we get rid of that 1/3? To take that 1/3 out, just like a cube root, I would cube both sides. Same thing here. Cube, cube. That cancels all that to get x, which is what we originally were looking for. 5 cubed is 125. That goes away to an x, and then 2 cubed is 8. And we have that. Okay? So again, be very, very careful when we're dealing with these let statements. They're very useful, very powerful tools, but if you're not careful to unpack them at the end, that can spell disaster in these problems. Okay, so make sure you unpack that box you created in the beginning. Okay, so what we're going to go to now is just a couple of applications. Again, nothing new. These are just applications we've seen in the past. We're going to see them though using different equations, more quadratic based as opposed to just general linear equations. Okay, so let me clean this up. Let's now go to practice 6. Practice 6 is found on page 685, and it says, together, Katie and Steve can groom all the dogs at the Bark and Doggy daycare in 4 hours. Alone, Katie can groom the dogs 1 hour faster than Steve can groom the dogs alone. Find the time in which each of them can groom the dogs alone. Now, we've seen this back in chapter 7 when we were dealing with work problems. When we have two different people doing a job and then they join forces and they get the job done together. Okay, so again, if you have to read these 2-3 times just to get an idea of what's going on, that's okay. Do that. Do whatever it takes to understand the situation. Then you start making a plan for the attack. Since this is a work problem, I'm always going to think of the two different people. So I have Katie joining forces with Steve, and they're getting the job done together. It is always going to be 1 over the time, 1 over the time, 1 over the time. Okay? The only time that that's going to be different is if someone's like going twice as fast or something like that, or doing half the job. That's the type of thing that we're going to have to adjust there. But we're keeping it simple right now. So it says, together, Katie and Steve can groom all the dogs in 4 hours. So together, it's 4 hours. Okay? Then it says, Katie can groom the dogs 1 hour faster than Steve can groom the dogs. Now, what I see a lot of people do is this. Katie can do this 1 hour faster. So I don't know how long Steve does, but then faster they say +1. But that's not really how time works when it's faster. If it's faster, that means it should be less time. So be very careful with that, because again, intuitively we think faster is more, but it's less time. So if you're not sure, throw some dummy numbers in there. Okay, like just some random numbers. Okay, so if let's say Steve is 6 hours, if she's faster, she would be 5 hours. If he's 11 hours, she should be 10. So we're not adding 1. We're subtracting 1. Okay, so we've got these right here. This is your equation we need to now solve. I am going to multiply through by the LCD. Now, one thing before I go any further, I could put an x here and then an x plus 1 here, whichever you prefer. Okay, if let's say you really want to avoid that negative, put the x plus 1 there instead. Okay, so we've got 4x, x minus 1, and we got that. These are gone. We've got 4x. This is gone. We've got 4x minus 4. Okay, after I distributed that 4 into that. Here the 4 is gone, so I have x squared minus x. Okay? Now, from there, I can combine these up, and I have 8x minus 4 is x squared minus x. And now again, I have a quadratic. Let's get that 0 on one side. I'm going to subtract 8x, add the 4. So 0 is x squared minus 9x plus 4. Now, if you look, that is not factorable. Okay, there's no way we're going to multiply to a 4 and then add to a 9. So I'm going to go into that quadratic formula. Opposite of b, plus or minus, square root, b squared minus 4ac all over 2a. So I have positive 9 plus or minus the square root of negative 9 squared minus 4ac all over 2a. 9 plus or minus square root of something over 2. And what we get, negative 9 squared is 81. 4 times 4 is 16, so 81 minus 16. 81 minus 10 is 71. 71 minus that extra 6 is 65. And we have that. Okay? Now, in this case, they are not telling us to round. They didn't say that you had to round this. So what they wanted to find was the time in which each of them can groom these dogs alone. This X we just found was a time for Steve. Okay? There's technically two answers here. So for Steve, we could have either 9 plus root 65 over 2 or 9 minus root 65 over 2. Okay? Now, Katie then can do this 1 hour faster, or it's subtracting 1 from that time. So let's see how that plays out. So if we subtract 1 from here, that would be 9 plus root 65 over 2 minus 1. Then over here, it's 9 minus root 65 over 2 minus 1. Okay? Now how do we work with that minus 1? Don't just leave it like that. A 1 can be thought of as 2 over 2. So what we're going to do is combine like terms across the top. That turns into 9 minus 2 is 7 plus root 65 over 2. And here, same thing. This 1 is a 2 over 2. 9 minus 2 is 7 minus root 65 over 2. Okay? Now, that's a lot of different answers that we have to work with. You could plug these in the calculator, get a decimal approximation to see what works, or let's think about this a little bit. Let's exercise our brains a little bit on this one. Okay? This, when we deal with times, what is one thing that we definitely want to avoid? When we have times, we want to avoid negatives. This is not negative. Everything's just positive there. Over here, what's the square root of 65? Okay? Square root of 65 is in between what? Square root of 64, right? 64, square root of 64 is 8. Square root of 81 is 9. So it's going to be 8 point something, right? Because it's between 64 and 81. So it's going to be 8 point something. If we go 9 minus 8 point something, this is still positive, isn't it? That's a problem because now we have two positive answers. Let's go down to Katie's times. Again, all positive. But here, square root of 65 again is what, approximately? You don't need a calculator for that. Perfect squares, 64 and 81. 65 is between there, okay? Square root of 64 is 8, square root of 81 is 9. So it's going to be 8 point something. 7 minus 8 point something, there's your negative. So this answer was garbage, not because this was negative, because it gave us a negative time later on. So this and this are both garbage. Because Steve can't have this time, because then based on the situation, Katie has a negative time that we can't have. Okay? So these are the times it's going to take. If you want to plug that in the calculator, get a decimal approximation, that's perfectly fine. But again, when you plug it in, like this one for instance, make sure you have parenthesis 9 plus square root 65. Close the square root, close the numerator, then divide by 2. Okay? And I believe on that one you should have approximately 8.5 and this one 7.5. Okay? again, in the grand scheme of things, if this was a real life application, we would want to have that decimal approximation. You don't tell your customer or your boss saying, I worked this many hours. But when we're doing calculations, try to get used to using these, because if we calculate with approximations over 3 or 4 steps, then they become very inaccurate approximations. Try to keep this as accurate as you can for as long as you can. Okay? Let's look at one more to finish this section up. Okay, practice 7 is found on page 686, and it reads, the 36-kilometer S-shaped Hangzhou Bay Bridge is the longest cross-sea bridge in the world, linking Ningbo and Shanghai, China. A merchant drives over the bridge one morning from Ningbo to Shanghai in very heavy traffic and returns home that night, driving 50 kilometers per hour faster. The total travel time was 1.3 hours. Find the speed to Shanghai and the return speed to Ningbo. Okay? So again, I read through it once just to get an idea. You have someone going into the city and then back out of the city. It's just their morning and evening commute. Okay, but what they're giving us are distances, speeds, and times. So this brings us back to this. Okay. Now the two different scenarios were that into the city, back out of the city. So we were going to Shanghai, and then to Ningbo. Okay. Now in the past, what I said before is gonna apply here as well. We have 3 categories of information. One will be given, one will be described, and then we're going to combine those 2 to get the third. Okay? So again, it says 36-kilometer S-shaped Hangzhou Bay Bridge is the longest cross-sea bridge in the world, linking Ningbo and Shanghai, China. That's just setting up the stage, but it does say there's 36 kilometers, so keep that in mind. A merchant drives over the bridge one morning from Ningbo to Shanghai in very heavy traffic and returns home at night driving 50 kilometers per hour faster. So he went from Ningbo to Shanghai at some speed. I have no idea how fast he was going. But when he came back home to Ningbo, he was going 50 kilometers per hour faster. Okay? Total travel time was 1.3 hours. Find the speed to Shanghai and then to Ningbo. Okay, so we still have distance and time up in the air. They did mention that it was a 36-kilometer bridge, and then that the total travel time was 1.3 hours. When we say total, that does not mean time here and time here individually. So we can't put anything in here right now. But what we can say is when he was going over the bridge in the morning, he was covering 36 kilometers. When he was coming home, going over that same bridge, he also covered 36 kilometers. Okay? Now, they described this. You could introduce a second variable with time here, but if we can avoid a system, avoid a system. So what I'm going to do is say that while distance equals rate times time, time is distance over rate. Okay, so this time can be described as 36 over r, and this time can be described as 36 over r plus 50. Okay, now what did they say about the time? The total time for travel was 1.3 hours. So when I take the time he traveled in the morning and the time he traveled in the evening, total, he was traveling for 1.3 hours. Okay? And now there's my equation. Remember, just like in the past, these things that we built, where it was a combination of the other two, This is typically where we're going to find our equation, whether we add them or set them equal or whatever it may be. And now we solve that. So what I'm going to do first is I'm going to clear those fractions. So I'm going to have r times r plus 50 r is gone. Okay? Then I distribute that 36, and I've got 36r plus, if you have to, remember, 36 times 50. Do you see how I put that 0 off to the side? Because then I get 30, 15 is plus 3 is 18, and I carry that 0 down. If you can do that in your head, that's great, okay? Another way you could do that is say 36 times 100 is 3600, then cut it in half, because 50 is half of 100, okay? And you've got 1800 there. Now, this is gone, so we just have 36r. And then on this side, we have, distributing the r, we've got r squared plus 50r, but then distributing that 1.3, and then 1.3 times 50, again, 1.3 times 50 is a 15, and 6, carry that down, bring that over, so we've got 65r. Okay? Now, we have a quadratic, so we want to get a 0 on one side. So since this is positive here already, I am going to get this stuff over here. First, we can say 72r plus 1800 equals 1.3r squared plus 65r. Subtract the 72r and the 1800. (65 minus 72 is negative 7r minus 1800. Okay? Now, this is a situation where I would most definitely just go right into the quadratic formula. I wouldn't spend too much time trying to clean that up with factoring or anything. Not to say it's not possible, but I would just go right to it. So, I'm looking for r this time. Okay? Opposite of b is a positive 7. Plus minus square root of negative 7 squared minus 4 times 1.3 times negative 1800. All over 2a. 7 plus or minus square root of something over 2.6. And then I would pick up the calculator here. And what we get, no square root just yet. Just say negative 7 squared minus 4 times 1.3 times negative 1800. And what we get is 9,409. Okay. Now, in this case, it says find the speed of Shanghai and return speed to Ningbo. So they didn't say anything about rounding or anything like that. But with a 9409, if we take the square root of 9409, we get a nice clean 97. Okay, so what that turns into is a 7 plus or minus 97 over 2.6. And then we can work that out. 7 plus 97 over 2.6, 7 minus 97 over 2.6. Now remember, these are talking about rates, okay? Can we have a negative rate? No. Whatever this ends up being, we know it's negative because 7 minus 97 is negative 90, so that's gone. The only thing we have to calculate is that top one. So 7 plus 97, divide that by 2.6, and we get 40. Now remember, that 40 is a speed, so that is kilometers per hour, and that was R. R was in the morning to Shanghai, okay? And then when we return home to Ningbo, we're going 50 more than that, so 40 plus 50 is 90 kilometers per hour. Specify which is which, even if it's just a short abbreviation like that. Okay, so this section had a lot. We talked about quadratic methods, which brings back rational equations, radical equations. We introduced that let statement. Okay, and then we went and looked at a couple of old application problems we've seen in the past. But again, it's just quadratics that may not be factorable. Sometimes they are, sometimes they're not. Okay, so again, just now we have everything at our disposal. If it's a quadratic, I still would get 0 on one side because you can factor still, or if that's not possible, you have that quadratic formula ready to go. Okay, so take your time, be careful, work on those let statements because those are new, but otherwise just trust the process, be focused on your arithmetic, and you'll do great. Okay, so as always, work hard. Let me know if you have any questions. I'll see you guys next time.